Hi, we are the House Knights team, and this is our net zero single family home design for a home in Orlando, Florida. I am Ross Batia, the team lead.
I'm Claire Huffstetler, the project manager.
I'm Kirill Mangual, second lead.
I'm Martin Lucas Valles, and I'm secretary.
I'm Tyler Marks, and I'm the researcher.
And Mr. Parahovnik is our advisor.
Upon closer examination of community issues, we identified Orlando's high housing costs, lack of energy savings education, and the gap between new and older homes. The home's current home score is 128, whereas newly built homes in Florida typically aim for a score of 100. Our objective is to achieve a HERS score of 41, aligning with the Department of Energy Zero Energy Ready Home Standards. Orlando's population continues to grow at record-breaking numbers. In this particular area, we found 10 newly built communities within a 12-mile radius, with one community building 3,486 new homes. The influx of people moving into Orlando is causing local residents to be in a tough financial situation. As families with larger salaries are moving in, a 3-bedroom, 2-bath home can cost over $500,000. LivingWage.com says that a family of 2 working adults with 2 children will need a living wage of over $105,000 to live comfortably in Orlando. But according to census.gov, the average household makes only about $66,292. This income would only qualify you for a home loan of $127,000.
Unfortunately, this influx and balance is happening to more and more longtime local residents. Our client, the Mangual family, falls under this income bracket along with many other families throughout the Orlando area. They purchased and built this 3-bedroom, 2-bath home in 1998 for $91,000, and it is now worth $385,000. When evaluating the home, one of the first major deficiencies we noticed is the lack of renovation and improper shading. What is our solution? It involves retrofitting the existing home as it is more cost-effective for the clients. This approach enables them to upgrade materials and technology while simultaneously reducing their carbon footprint.
This home is located in Climate Zone 2A, with some of the biggest issues being high year-round temperatures and humidity. These effects are amplified by the reduction of trees and heat being retained in concrete. The current energy use of the home is shown by month in the graph, with specifically the summer and fall months showing significantly higher energy usage, causing the HERS score to come out to be 128 and carbon index of 130. This is higher than a standard new home, which normally has a HERS score of 100. Now moving on to our primary objectives. Our main project goals are to create a net zero energy home, reduce internal heat gain, ensure affordability, and instill energy mindfulness. In order to meet our design goals and fulfill all requirements for a zero energy ready home, we reference the standards shown throughout the design process. The zero energy ready home and HERS index ensures that efficient appliances, fixtures, and practices are used to reduce the total energy usage of the home before implementing renewable energy to bring the home to a net zero design. Here are several components of our design we will be focusing on in order to improve overall energy efficiency and meet our design goals.
To achieve net zero design, prioritizing effective power generation is key. Though we explored geothermal and wind energy, they proved impractical for this home. Living in sunny Florida, an 8.5 kilowatt solar system coupled with a 13.5 kilowatt hour battery ensures sustained energy supply, even during periods of limited sunlight. With the addition of a smart electrical panel, the home becomes fully connected and the homeowner can budget their energy use. The SPAN Smart Panel can reduce up to 15% on energy bills and helps regulate energy usage for EV charging. Based on Google Project Sunroof data, this home receives approximately 1,739 hours of sunlight annually. Unlike some locations where lifting solar panels to specific angles optimizes their performance, Florida's abundant sunlight and the home's modest energy usage make it unnecessary for this design.
The home currently has a split system with a SEER score of 14. To improve this, we propose to switch to a system with a heat pump that has a SEER score of 23 and an HSPF score of 11.8. The SEER and HSPF score is a way of measuring the efficiency of cooling and heating equipment, respectively, where higher scores indicate more efficient systems. To help relegate this system, we can use the ENERGY STAR certified ecobee thermostat, which can save up to 23% on annual energy cost. With its smart features, one can control home temperatures from any smart device. If coupled with smart sensors, temperatures can automatically be managed with occupancy detection, helping balance your home's temperature for enhanced comfort. As for the building envelope, we plan to add fiberglass boards to the exterior walls to improve the R value from 4.10 to 16.50. Due to compression and moisture buildup, the insulation for the roof and ceiling should be replaced to maintain the R value of 30 for each.
The home's fenestration will undergo a complete upgrade to high-performance windows with improved U factors and solar heat-gain coefficients. Each fenestration is also marked with an IZ3 icon, meaning that these windows will hold up to Florida's hurricane-force winds. The garage door is made out of 4 layers, including 2 outer layers of steel, insulation, and a composite overlay to significantly reduce the amount of cracking and corrosion. Like the windows, the front door is made up of low emissivity glass, allowing mostly only visible light through while keeping the majority of the heat out. To reduce strain on the heating and cooling equipment, it is important to minimize heat transfer through the envelope and fenestration. We can utilize Fourier's law for a one-dimensional conduction heat transfer scenario to calculate for heat flux. By using these equations, we were able to prove that the home's upgrades reduces heat transfer by at least 75%.
Another means of reducing heat transfer from the environment is implementing passive design techniques. Proper shading is one of the most effective methods, so adding overhangs and window coverings was a necessary addition. Placement of trees and other shading provided by landscaping was also added to the final design despite the small lot size. Careful overhang design cuts summer cooling costs by blocking sunlight but lets it in during the winter to save on heating. For accurate design, location is considered to direct sunlight effectively year-round. NREL provides solar data as shown to find optimal overhang sizes easily, and adjusting for the precise location, proportions are calculated accordingly. All major appliances, ceiling fans, and vent fans are to be upgraded to ENERGY STAR rated products where needed. We also took into consideration how smart features correlate with energy savings. This is the process we use to compare different models for each component and apply a weighted rating evaluation to help make a final decision. Here's an example of a weighted rating evaluation we used. This one is for the refrigerator, but a very similar process is applied to all major home appliances, as well as roofing materials and HVAC systems. Each component has different criteria based on the function, but efficiency and cost were included in all evaluations. Upgrading the currently outdated water heater to a smart and efficient model will help manage hot water use and temperatures effectively. Replacing it with this model that has a uniform energy factor of 3.88 and adding WaterSense fixtures will contribute to significant energy savings. This simple self-installation water monitoring device can be useful by allowing one to understand how water is consumed in the home from your smart device. You can detect leaks, manage water use, and see a breakdown of usage from each household appliance and water fixtures.
Here's a glimpse of the potential interior, having an open floor plan seamlessly connecting the living room and the kitchen, followed by the guest bedroom, office, and master bedroom. After implementing energy-saving practices, our proposed design reduced the HERS from 128 to 40. Incorporating solar brought it down further to -51. Additionally, when looking at the carbon index, we showed that the home went from 43 to -21, which resulted in lowering our energy bill to approximately $1,400 without solar and $360 with solar. The total retrofit cost tallied over $148,000. Such investments allow the homeowner to earn back some of their expenses, plus enhance their home's equity value, making the energy efficient retrofits the wiser choice.
To make this design more accessible to people, we separated the upgrades by cost. Homeowners can alleviate costs through available tax credits and rebates. The federal government extends a 30% tax credit up to $3,200 annually, and there are local rebates aimed at promoting energy efficiency. Our main goal is to provide education on energy efficiency methods and products, so we plan to continue this project after senior design is over and develop a website to organize our research ensuring accessibility for all of Orlando residents. We truly believe in empowering everyone to contribute to Orlando's energy efficiency and enable residents to save money. Thank you.